The zinc atoms present in metal rod undergo oxidation, leaving behind 2 electrons. E of cell is equal to. With respect to this electrode, it is an electron deficient and has a tendency to take or gain column, which is filled with agar-agar jelly. The hydrogen acts neither as anode nor as cathode. Cell made up of lithium and hydrogen gas. Then the voltmeter reading shows 3.05 volt. The voltmeter shows the reading of 0.80 volt. The standard oxidation potential value, that is 0. Solution in both the electrodes is 1 molar. EMF or elements are arranged in the increasing or decreasing order of their standard reduction potentials. We can see deposition of silver over here and the solution is turning into pale blue. Flows in a circuit with higher intensity, concentration of the electrolyte. 1.1 volt was EMF, but 1.05 volt is a. Hello students, welcome to Learn It. As we discussed before, that study of electrochemistry is nothing but the study of electrochemical cells. There are two types of electrochemical cells. The first one is galvanic cell. Second one is electrolytic cell. So let us discuss with the galvanic cell. So galvanic cell is a device in which chemical energy of spontaneous redox reaction is converted into an electrical energy. Within this galvanic cell, there are chemicals. These chemicals undergo reaction to produce what? Some products plus energy. We are not bothered about the products, we are only bothered about the energy. And the reactions are spontaneous. It means these reactions happen by themselves without any external influence. The galvanic cell is also called as voltaic cell. So let us look at the components of the galvanic cell. Galvanic cell contains two electrodes. One is negatively charged, another one is positively charged, which are connected by salt bridge. At the negative electrode, the electrons are generated. At the positive electrode, the electrons are consumed. Next question comes, what is an electrode? So let us learn it with an example. Consider a zinc metal. It is in contact with dilute solution of zinc. So the dilute solution of zinc containing Zn+2 ions. So when zinc is in contact with its own ion and the concentration of the zinc is less, that time the zinc atoms present in metal rod undergo oxidation, leaving behind 2 electrons on the zinc rod. So because of this oxidation process, there will be accumulation of electrons on the zinc rod. Before, the rod was electrically neutral, but because of this oxidation, there will be accumulation of electrons on the zinc rod. Now this rod is said to be an electrode, and this electrode is electron rich, and because there is an excess of electrons, this has a tendency to give or lose or donate those electrons, and this tendency is called as oxidation potential. And as the electrons are accumulated, this rod is negatively charged. And the electrode where oxidation takes place is called as anode. So that's why this is an anode. So zinc metal becomes anode when oxidation takes place. And when does this oxidation takes place? This oxidation takes place when zinc rod is in contact with dilute zinc solution. So how to represent this zinc anode? This is representation of zinc anode. So zinc, which is solid, bar, it means it is in contact with Zn+2 ions, which is having certain concentration. Let us look at the positive electrode. The question comes, how does that electrode consume an electron or electrons? Let us learn with an example. When the same zinc rod is in contact with excess of ions, then the ions, that is Zn+2 ions present in the solution, start to gain the electrons from the atoms on the metal rod. So in turn, these Zn+2 ions become atoms. So this conversion of ions, cations, to atom by the consumption of electron is called as reduction. We have already seen the conversion of ion into atom by the consumption of 2 electrons from the neighboring atom. So this ion may take 2 electrons directly from the one atom or 1 electrons from the neighboring atoms. So this accepting of electrons from the neighboring atoms continues. So that's why when zinc metal it is in contact with excess of Zn+2 ion, there will be reduction. Due to the reduction, the size of the metal rod increases, but there will be deficiency of electrons in the rod. Hence this rod is called as electrode. With respect to this electrode, it is an electron deficient and has a tendency to take or gain or accept the electrons, which is called as reduction potential. Is positively charged. The electrode where reduction takes place is called as cathode. Representation of zinc cathode as follows. Zn+2 ion having certain concentration C is in contact with zinc, which is solid. In conclusion, when a metal is in contact with dilute solution of its own ion, then there will be an oxidation, which leads to electron-rich electrode called as anode, which is represented by the metal which is in contact with its own ion having certain concentration. During this process, metal atom is converted into cation. With respect to electrode, the dissolution of the electrode material takes place, size of the electrode decreases, electron accumulation on the electrode increases, tendency of an electrode to donate the electron, that is, oxidation potential, increases. When same electrode it is in contact with concentrated solution of its own ion, reduction takes place, which leads to electron deficient electrode called as cathode, which is represented by a metal ion having certain concentration is contact with metal. During this process, the cation is converting into metal atom. With respect to the material of the electrode, the deposition of the material on the electrode takes place, size of the electrode increases, electron consumption in the electrode increases, tendency of an electrode to accept the electron, that is, reduction potential, increases. Next question comes, until what this reaction, that is, the oxidation or reduction process, continues. So this oxidation or reduction process continues. It depends upon the concentration of the solution. But this oxidation or reduction process continues until the concentration of the solution becomes equilibrium concentration. So the next component of galvanic cell is salt bridge. So salt bridge is a device which connects anode to cathode. The salt bridge contains a saturated solution of potassium chloride or potassium nitrate or sodium nitrate or ammonium nitrate, any one of them, which is prepared in agar-agar jelly or gelatin. The functions of salt bridge are: first one, it completes the electric circuit. Second one, it maintains electrical neutrality in the solution of two electrodes, and these two electrodes are also called as half cells. In conclusion, salt bridge is a column which is filled with agar-agar jelly, but these agar-agar jellies are dipped in solution of KCl or potassium nitrate or sodium nitrate or ammonium nitrate as shown in this picture. We discussed about when zinc rod it is in contact with dilute solution of its own ion, that is Zn+2, then there will be oxidation, and when the same zinc rod it is in contact with concentrated solution of Zn+2 ions, then there will be reduction, and the process of oxidation and reduction continues until the concentration of the electrolyte becomes equal to equilibrium concentration. So now the question comes, what if the concentration of the solution becomes 1 molar and we take different electrodes like zinc, lithium, copper, silver and lead? At this time, what will happen? So, called as electrodes. And when we maintain the temperature of the surrounding 298 Kelvin and the pressure at 1 atmosphere, so this condition is called as normal temperature and pressure. When we maintain it, then all these are called as standard electrodes because we have established a standard condition. Hence, at this condition, the zinc will undergo oxidation to become anode. The same way, the lithium will also become an anode, but opposite way. The copper +2 ions start to deposit on the copper, and this copper will become cathode. Same way, the silver will also become a cathode, and lead will also become a cathode. This is because the nature of the electrode material. So next question comes, what if we take the gaseous material like chlorine and hydrogen? So these two are also maintained at normal temperature and pressure. So here the chlorine gas is filled in this inverted tube at 1 atmospheric pressure. Same way, hydrogen is also filled in inverted tube at 1 atmospheric pressure. And both the solutions are containing 1 mHCl. But here we are considering the Cl minus, here we are considering the H plus. Here we can see the reaction can only takes place between the junction of this gas and this liquid. So that's why, so as to curb this difficulty, we introduce a system which is made up of platinum plate which is connected to platinum wire. At this time, the reaction takes place on this platinum plate. Then what will happen with the chlorine? Whether it will be cathode or anode, that we will see. We know that chlorine is an electronegative atom or electronegative element. So that's why chlorine will undergo reduction. So that's why chlorine acts as a cathode. The interesting phenomenon happens with respect to hydrogen electrode. There are two possibilities. First one, the hydrogen can act as an anode. The representation is like this. Or it can act as a cathode. But at this normal temperature and pressure or standard condition, the hydrogen acts neither as anode nor as cathode. And we know that it can easily undergo oxidation, that is, hydrogen can easily undergo oxidation into H plus ion, or H plus ions can become hydrogen. We use this standard hydrogen electrode as a reference electrode. Reference electrode means we use standard hydrogen electrode for measuring the potential other electrodes. So let us see with an example. So we know that both zinc and lithium electrodes act as anode. But the question comes, in between zinc and lithium, which electrode has more tendency to donate the electron, which is called as oxidation potential? And second one is how to measure it. The answer is, we take the zinc electrode and connect it with the standard hydrogen electrode. Here both the electrode materials are connected through wire. In between them voltmeter is placed, and both the solutions are connected by salt bridge. So this constitutes a cell. So here the function of salt bridge is it completes the circuit and it maintains the electrical neutrality. So we will see the working of cell. So here we know that zinc will undergo oxidation at NTP, but hydrogen, it acts as anode also cathode. But in this case, when zinc is acting as an anode and it is producing electrons, these electrons travel through this wire and enter into the platinum wire and sit on the platinum plate. Then the H plus ions present in this acid or this electrolyte gains those electrons and convert into hydrogen gas. So zinc will undergo oxidation, hydrogen will undergo reduction. So zinc acts as an anode, hydrogen acts as a cathode. And the voltmeter here shows how much zinc is having more oxidation potential. So this voltmeter shows the reading, that is 0.76 volt. It means the zinc is having oxidation potential 0.76 volt than the hydrogen. So this cell can be represented as zinc, which is solid. It is in contact with Zn plus 2 ions, which is having the concentration 1 molar, which is connected by salt bridge. This double bar indicates the salt bridge, which is in contact with H plus ions, which are having the concentration 1 molar, which is in contact with hydrogen gas, which is connected to platinum. Here the left hand side indicates the anode, which is connected to, this is anode, which is connected to cathode through salt bridge. So if we take this cell, so I have already told this is a cell. If we take the cell, which is made up of anode zinc and cathode hydrogen, which are connected by salt bridge, it will measure the voltage 0.76 volt. But in reality, it doesn't exist. it is a hypothetical cell. So the anodic reaction is oxidation, that is zinc will convert into Zn+2 ion and gives the 2 electrons. So the concentration of this anodic solution increases. In the cathode, when these 2 electrons come, they will sit here. These 2 H plus ions in the acid takes those 2 electrons and they will convert into 1 molecule of hydrogen. So there will be evolution of hydrogen. So in the anode side, the zinc will be dissolved. In the cathode side, the hydrogen gas is liberated. So this is the cell reaction. So instead of this, if we take the zinc rod and we put this zinc rod in the acid, this is H plus means acid, then this cell constitutes, which is having the potential 0.76 volt. So that time the zinc will undergo oxidation, means zinc dissolves in the acid and simultaneously hydrogen gas is liberated. So this is the reaction. In the same way, if we connect lithium electrode with hydrogen electrode, here the voltmeter shows the reading of 3.05, which is higher than the zinc, because we already know that lithium is the most electropositive element. So lithium wants to undergo oxidation. That's why lithium has more oxidation potential, that is 3.05 volt, than the zinc, which is having 0.74 volt. Remember, this 3.05 volt and 0.76 volt are potentials, because these two generate the electrons and give the electrons to hydrogen electrode. So cell representation is same like zinc. The lithium, which is solid, in contact with lithium cation, which is having the concentration 1 molar, which is connected to salt bridge, which is connected to hydrogen ion or acid, whose concentration is 1 molar. It is connected to hydrogen gas, which is connected to platinum wire. So here lithium acts as an anode, which is connected to cathode through salt bridge. So if we take the hypothetical cell made up of lithium and hydrogen gas, then the voltmeter reading shows 3.05 volt. The anodic reaction involves the lithium undergoes oxidation to form lithium plus ion and 1 electron. And the cathodic reaction is when 2 hydrogen ions react with, or when they gain 2 electrons, there will be formation of hydrogen gas. The overall reaction, which is balanced, it means that atoms should convert into lithium ions, which will liberate 2 electrons, and they travel through this wire and sit on this platinum plate. After that, the 2 H plus ions, they gain those 2 electrons and become hydrogen gas. Or when we put lithium metal in an acid, there will be formation of lithium cations. It means the lithium dissolves in the acid simultaneously there will be evolution of hydrogen gas. So in conclusion, we can see a standard electrode potential which is represented by the symbol E0, which is always calculated at NTP. So with respect to hydrogen, E0, that is hydrogen, is converted into cation. It means oxidation potential, that is standard oxidation potential of hydrogen electrode is 0 volt. Similarly, E0, that is cation to molecule, it means reduction. So standard reduction potential of hydrogen electrode is 0 volt, because we already know that at NTP in the hydrogen electrode there will be no oxidation and no reduction. So standard electrode potential E0 with respect to zinc we have already discussed. So E0 of zinc, that is Zn, is converted into Zn plus 2, means oxidation. So standard oxidation potential of zinc is 0.76 volt. Similarly, with respect to lithium, standard oxidation potential of lithium is 3.05 volt. So by this we can conclude that lithium has more standard oxidation potential than zinc. Similarly, we need to discuss about the electrodes which undergo reduction at NTP. It means the electrodes which are cathode at NTP. So we know two examples. First one is copper, second one is silver. So thus the question comes, between copper and silver, which electrode has more tendency to accept the electron, or which has more reduction potential? And the second question is how to measure it. So as before, we measure it by using standard hydrogen electrode. So we take the copper electrode and connect it with the standard hydrogen electrode. So here the platinum wire of standard hydrogen electrode is connected to copper by external wire. In between them the voltmeter is placed. Circuit is not complete because these solutions are not in contact, so that's why we use the salt bridge. At this time the voltmeter shows the reading of 0.34 volt. Here the hydrogen is undergoing oxidation because the copper is undergoing reduction. So standard oxidation potential of hydrogen is 0 volt. So it means that this 0.34 volt is the standard reduction potential of copper electrode. This cell is represented by the symbol platinum, that is this platinum wire. It is in contact with the hydrogen, which is the gaseous state, which is in contact with the H plus ions whose concentration is 1 molar, which is connected to salt bridge, so which is represented by double bar, which is in contact with copper plus 2 ions whose concentration is 1 mole, which is in contact with copper, which is solid. So here left hand side is anode, so hydrogen acts as an anode which is in contact with the cathode, that is copper electrode, through salt bridge. If we take the hypothetical cell in which anode is hydrogen, cathode is copper, so if we connect the voltmeter, then it shows the reading of 0.34 volt. So the same cell is represented here. So at the anode there is an oxidation, so hydrogen is converted into H plus ions. It means that hydrogen gas converted into H plus ions. So the concentration of H plus ions increases. There will be increasing H plus ion concentration. So at the cathode, the copper will be deposited. It means that Cu plus 2 ions starts to deposit. You can see here. So the overall reaction is the hydrogen, that is hydrogen gas, is converted into H plus. So it means that it is giving the electrons. So these electrons come and sit here, and so these electrons are taken by Cu plus 2 ions. So as we discussed before, what if we take copper and we put it into acid? So this is an acid. H plus ions means acid. So when we put copper, there will be no reaction, because we know that copper wants to undergo reduction, not the oxidation. So that's why this reaction doesn't happen. Similarly, when we take hydrogen electrode and connect it with the silver electrode, here we are going to connect hydrogen, that is platinum wire, with the silver. In between them, voltmeter is placed and the solutions are not in contact, so we introduce the salt bridge. So this time the voltmeter shows the reading of 0.80 volt. This 0.80 volt is the standard reduction potential of silver electrode. This cell is represented by platinum, which is in contact with hydrogen, which is in contact with H+, which are connected to salt bridge, which are in contact with silver ions, whose concentration is 1 mole, then silver, which is solid. So here hydrogen acts as an anode, silver acts as a cathode. So if we take hypothetical cell, so this is already a cell, but we are taking it as an example. So if we take a cell in which one part, that is anode, is made up of hydrogen electrode, cathode is made up of silver electrode. If we connect the terminals of this cell to voltmeter, then voltmeter shows the reading of 0.80 volt. So here anodic reaction is again the same, that is decomposition of hydrogen into H+ ions. In the cathode, silver is deposited. So this is the overall redox reaction. So if we take the acid and if we put the silver, then there will be no reaction, because silver wants to gain the electron and H+, that is hydrogen, wants to undergo oxidation, but here no hydrogen, H2 is not there, and here no Ag+, so that's why there is no reactant side, only products are there. So backward reaction is not possible. In conclusion, if we look at the standard electrode potential E0 for copper, represented as Cu plus 2, is converting into Cu. It means that cation is converting into atom. So this shows standard reduction potential. So standard reduction potential of copper is 0.34 volt. Similarly, if we look at the standard reduction potential of silver electrode, then it is 0.80 volt. It means the standard reduction potential of silver is more than the standard reduction potential of copper electrode. It means the silver wants to undergo a reduction more than the copper. So until now we discussed about the two types of standard electrode potential. The first one is standard oxidation potential. The second one is standard reduction potential. So let us arrange them. So here hydrogen is at the middle because it is having the standard reduction potential or standard oxidation potential whose value is 0. Copper, whose standard reduction potential value is 0.34 volt. So it is above the hydrogen, but it is below the silver because it is having the value 0.80 volt. The zinc is having the standard oxidation potential value, that is 0.76 volt, but it is below the lithium. So if we add some more elements like fluorine, because we know fluorine is the most electronegative element, then it will occupy the position first in the standard reduction potential value. And the lead, it comes between hydrogen and zinc, whose value is 0.13. It is standard oxidation potential. So here, if we analyze, the lithium is having the highest standard oxidation potential value. So this is one of the reason why lithium batteries are efficient energy storage devices. So as to curb the confusion of standard reduction potential and standard oxidation potential, we come across the consideration that convert all the oxidation potential value into negative of reduction potential. It means that lead, which is having the 0.13 oxidation potential value, converted into negative of 0.13 volt. It is understood that negative values indicate the standard oxidation potential. So we get a list. Here the elements are arranged in the increasing or decreasing order of their standard reduction potentials. And this arrangement is called as electrochemical series. Here we have the bigger electrochemical series. As the space was not available, I put into 2 slides. So we can see hydrogen is at the bottom. It means that all the elements above it are having the positive standard reduction potential. Fluorine is at the top. Here it indicates the reaction. Here it is the standard reduction potential value. And this list is in the decreasing value of standard reduction potential. So here the hydrogen is at the top, means that all these elements are having the negative value of standard reduction potential. You can see lithium is at the bottom, whose reaction is this, and the standard reduction potential value is minus 3.05 volt. As far as the competitive exams are concerned, electrochemical series is the important segment. So students must understand 2 things. First one, fluorine is at the top and lithium is at the bottom. So this is the first thing. And with respect to fluorine, it is the most electronegative element. Lithium, it is the most electropositive element. These 2 things students must know. And what is an electronegative element? Electronegative element can be easily understood by one example. Consider any metal which approaches to fluorine. Then this fluorine takes the electron from this metal forcefully. It means that this fluorine makes this substance to undergo oxidation. Then fluorine acts as an oxidizing agent. But with respect to lithium is having 1 electron. It is 1s2 2s1. It doesn't want this electron. So if it is approached by any substance or any other metal, then it forcefully gives this electron to that. So it makes, this lithium makes other substance to undergo reduction. So that's why lithium is the strongest reducing agent. So at the top we have the oxidizing agent, at the bottom we have the reducing agent. With the help of this knowledge, we are going to our next study, that is applications of electrochemical series. It means what is the use of this electrochemical series. The first one is to predict the relative strengths of oxidizing and reducing agents. Second one is to predict the feasibility of a reaction. Third one is calculation of EMF of the cell. Fourth one is to predict whether a metal can liberate hydrogen from acid or not. So let's discuss the first one. We can predict the relative strength of oxidizing and reducing agents by using the electrochemical series. So here it is already given that oxidizing strength, it is in the order of H2O2 is at the first, then KMnO4, then K2Cr2O7. So oxidizing strength of hydrogen peroxide is more than the KMnO4 than the K2Cr2O7. We can confirm it by using the electrochemical series. So here we already know that oxidizing strength is highest at the top. So we need to check from top to bottom whether the series is correct or not. So here at the third position we have hydrogen peroxide. So hydrogen peroxide is number 1. Then comes the MnO4 minus. So MnO4 minus, it comes from KMnO4. So it is at the second. Next comes the K2Cr2O7, that is Cr2O7 minus 2 comes from K2Cr2O7. This is at the third. So by this electrochemical series we can predict the relative oxidizing strength. In another way we can discuss this relative strength of oxidizing and reducing agent is by using the values. So they may give like E naught of MnO4 minus 2 Mn plus 2. Here the student must know or predict what is the change in oxidation state. So here it is plus 7, here it is plus 2. So plus 7 to plus 2 means it is a reduction. So plus 7 to plus 2 means there will be accepting of 5 electrons. So it is reduction. So if they give like EMnO4 minus 2Mn plus 2, then it is the standard reduction potential. Its value is 1.49. So with respect to relative strength of reducing agent, we know lithium is the strongest reducing agent. So any reducing agent with lithium, like lithium aluminum hydride, it is the strongest reducing agent. Then we already have sodium in ethyl alcohol. It is less stronger reducing agent than lithium aluminum hydride. The relative strength of reducing agents is used in metallurgical operations or in the purification of metals from metal oxides. So here we have aluminum oxide. It is called as alumina. So from alumina to aluminium we use reducing agent. So how to select the reducing agent? So here it is the aluminium, and all the metals which are below this aluminium in this electrochemical series can act as a reducing agents. So we can use the magnesium, we can use the calcium, we can use the barium, because others also can be used but they are having the negative impacts. So here generally magnesium is used. It means magnesium metal is used. Second application of electrochemical series is predicting the feasibility of a reaction. So here we have copper solid which is in contact with aqueous Ag plus ions. It means we have Ag plus solution, in that copper rod is inserted. This is a redox reaction. Whether this reduction is possible or not can be predicted by using the electrochemical series. We know that Cu plus 2 to Cu can happen. That we know that E naught of Cu plus 2 to Cu is having the value 0.34 volt. In the same way, E naught of Ag plus to Ag, which is having the value 0.80 volt. So it means the reduction potential of silver electrode is more. Silver electrode is more. Means that when Ag plus ions are in contact with copper, then they can grab the electrons from copper. So this reaction is feasible and it can be understood by this graphical image. Here this solution is containing Ag plus ions and this is the copper metal. We can see deposition of silver over here and the solution is turning into pale blue. So pale blue indicates the Cu plus 2 ion. So there is an oxidation of copper into Cu plus 2 and reduction of Ag plus ion into Ag simultaneously. But when we put silver rod into copper plus 2 solution, this reaction doesn't happen. Next application of electrochemical series is calculating the EMF of the cell. So consider the cell. It is never used before and the potential difference between the terminals of this electrode is called as EMF. Because it is never used, it is the highest potential difference between the terminals of the cell or battery. So EMF is more in the beginning, but then when we start to use the EMF, this is EMF, but when we start to use it, its energy or its potential difference decreases. Now this is called as potential of cell or cell potential. So EMF of the cell can be calculated by using the formula E naught of the cell. E naught of the cell is EMF of the cell, which is equal to E naught of cathode minus E naught of anode. So this is the Daniell cell. So Daniell cell consisting zinc and copper electrodes, which are connected by salt bridge. Here E naught of the cell, that is EMF of the cell, is equal to E naught of cathode. So here copper acts as a cathode and zinc acts as an anode. So standard reduction potential of copper electrode is 0.34 volt minus standard reduction of potential of zinc electrode is minus 0.76. That's why we get the 1.1 volt. Next application of electrochemical series is to predict whether a metal can liberate hydrogen from acid or not. So consider a vessel in which acid is present, which should convert into hydrogen from certain metal. So this H plus will convert into H2 by using this metal. It happens when this metal has to give an electron to H plus. When does this happen? So this happens when this metal should undergo oxidation. It means that this metal should be having oxidation potential, or it should have negative reduction potential. E naught for H plus to H2 is 0. So all the metals which are below standard hydrogen electrode can displace the hydrogen from acid. So this completes the applications of electrochemical series. Let us consider a cell made up of zinc and silver. It is externally connected to voltmeter. So by this cell representation, we can assume that left hand side, that is anode, is made up of zinc and cathode is made up of silver electrodes, and salt bridge is in between. So if we maintain the temperature and pressure as normal temperature and pressure, which is 298 Kelvin and 1 atmospheric pressure, and here the concentration of both the solutions is 1 molar, then we are talking about the EMF or electromotive force, which is represented as E naught of cell. It is theoretically calculated by the formula E naught of the cell is equal to E naught of cathode minus E naught of the anode, as we discussed in third application of electrochemical series. When we connect standard zinc electrode with standard silver electrode, TP, the voltmeter shows the reading of 1.56. This is practical value. Theoretically, it is calculated by using the electrochemical series. Here, standard reduction potential of zinc is minus 0.76. Standard reduction potential of silver is 0.80 volt. So that's why E naught of this cell is equal to 0.80 minus of 0.76, which gives 1.56 volt, which is same as the practical value. Let us consider another example in which anode is made up of copper and cathode is made up of silver, and here both the solutions are at 1 molar concentration. So we are talking about the standard copper electrode and silver electrode. So here the voltmeter shows the reading of 0.44 volt. So when we look into the electrochemical series, we get the standard reduction potential of copper, which is equal to 0.34 volt. As we have already discussed, the standard reduction potential of silver is 0.80 volt. So here both of them are having the positive standard reduction potential. Here the silver is having the more standard reduction potential. So when silver is in contact with copper electrode, the silver makes copper to undergo oxidation because the standard reduction potential of silver is more than the copper. So even though the copper is having the positive reduction potential, it will undergo oxidation because of silver. So when theoretically calculated, it gives the value 0.44 volt, which is equal to practical value. So let us take a cell which is made up of anode lithium and cathode fluorine. Lithium is at the bottom of the electrochemical series and fluorine is at the top of the electrochemical series. So when we connect both these electrodes, then voltmeter shows the reading of 5.92. So we know that E naught of lithium electrode is minus 3.05 volt and fluorine is 2.87. So E naught of the cell can be calculated by the formula, which gives the value 5.92, which is equal to practical value. So what is an EMF? Electromotive force is the maximum potential difference between electrodes of a cell. So these are two electrodes. Between them, the maximum potential difference, it can be 5.92 volt, or it is maximum work that can be taken out from a cell, provided cell is at standard conditions. So here standard conditions are maintained. That is, when we look into one example, that is Tesla battery. So these are the batteries used in Tesla cars. So the Tesla battery can give the maximum voltage of 3.6 to 3.7 volt. These are connected in series so as to get the potential difference of 500 volts. But with respect to lithium fluoride battery, practically it doesn't exist. In conclusion, we can look at all these three cells and compare the EMFs: zinc and silver electrode, copper and silver electrode, lithium and fluorine electrode. Here we can see 5.92 volt means the electrons flows in a circuit with higher intensity. So work done by lithium and fluorine cell is more. So let us look at new concept that is called as factors which affect the cell potential. The first one is material of the electrode. We have seen three examples in which we took zinc and silver, copper and silver, lithium and fluorine. In all those cells, the cell potential or the EMF was different. So students must know that EMF is the maximum cell potential. So in three examples, the materials of the electrodes were different. That's why the cell potential was different. Second factor is temperature. Temperature is a thermodynamic factor. So if the temperature changes, all the reactions get affected. So in the cells there are electrodes. If temperature changes, then the reactions in the electrodes get affected. Third one is concentration of the electrolyte. We know cell is made up of electrodes, and within the electrode there is an electrolyte. So as the concentration of the electrolyte changes, the cell potential also changes. This is an important concept, so let us look deep into it. Consider a cell which is made up of zinc and copper electrodes at NTP, and the concentration of the electrolytes is 1 molar. This is same as, so this cell is called as Daniell cell. Daniell cell is a galvanic cell having the electrodes zinc and copper. It may be 1 mole or it may be other than 1 mole. So when Daniell cell starts to operate, it means if we connect the bulb to the Daniell cell, then bulb starts to glow. Initially the voltmeter reading or the EMF is 1.1 volt. So as the time passes, the electrode reactions take place and the EMF is converting into cell potential. So 1.1 volt was EMF, but 1.05 volt is a cell potential. So cell potential starts to decrease as the time increases and the bulb starts to dim down. After a certain time, the bulb starts to glow. The electrons also stop to flow. So this is called as variation of cell potential. So it was 1.1 volt. So now it dropped down to 0. So what are the things that changed during this transition? This is called as variation of cell potential. So we use zinc anode. So let us learn with that example. First one, consider it is NTP. Here the zinc is connected to standard hydrogen electrode. So the voltmeter shows the reading of 0.76 volt. So 0.76 volt is the oxidation potential of zinc. But we know standard reduction potential of zinc is minus 0.76 volt. So the voltmeter has no negative reading, so it is showing the 0.76, and it is understood that zinc is undergoing oxidation. As the time passes, there will be variation of concentration of the electrolyte in the zinc because the zinc solid is converting into Zn+2 ion, or zinc starts to dissolve in this solution. The question comes, why zinc is undergoing oxidation? It is because thermodynamics. We know every spontaneous reaction is accompanied by change in Gibbs free energy. So Gibbs free energy is indicated by delta G. Here the reaction is happening by itself. It means a spontaneous reaction. This spontaneous reaction happens because of change in Gibbs free energy. It is given by the formula delta G is equal to delta G naught plus RT ln Q, where delta G is change in Gibbs free energy at conditions other than standard conditions. Delta G naught represents change in Gibbs free energy at standard conditions. R is real gas constant. T is temperature, which is measured in Kelvin. Q is reaction coefficient or reaction quotient. Here delta G depends upon all these factors, but delta G naught is specific for specific reaction. R is constant as it is real gas constant. T temperature is constant, it is 298, but variable is Q. So we need to know what is Q. The reaction coefficient Q is equal to concentration of the product divided by concentration of the reactant. With respect to above equation, the ln Q can be converted into log to the base 10 by multiplying it with 2.303. So with respect to this reaction, the Q equal to concentration of the product, that is Zn plus 2 divided by concentration of the reactant, means Zn. So Zn is solid. So concentration of the solid, or the logic of applying concentration term to the solid, is vague. That's why we neglect the concentration of the solid material, that is concentration of the zinc is neglected. So the concentration of zinc divided by 1. So in this condition, that is NTP, and the molar concentration of the electrolyte is 1. So this Q becomes equal to 1. So when we put this Q into above equation, we get delta G is equal to delta G naught plus 2.303 RT log 1 to the base 10, which is equal to delta G is equal to delta G naught, because log 1 to the base 10 value is 0. So this concentration term becomes 0. So at NTP, or at standard conditions, change in Gibbs free energy is equal to standard Gibbs free energy change. So here the question comes, what is the relationship between thermodynamics and electrochemistry? So here the reactions are happening by themselves. It means spontaneous reaction. So this spontaneous reaction makes this electrode potential to change. So it can be given by the formula. So the relationship between the change in Gibbs free energy and electrode potential is delta G equal to N minus NFE. So this is the relationship between the thermodynamics and electrochemistry. Here N is number of moles of electrons transferred, F is Faraday's constant, which is 96,500 coulombs per mole, E is electrode potential. I'll make a dedicated video so as to derive this relationship. So here we already know when concentration of Zn plus 2 is equal to 1, it means at standard condition we know that delta G equal to delta G naught. So the above relationship becomes delta G naught is equal to minus NF E naught, because at standard condition it was delta G naught. So at standard condition we say it as a standard electrode potential. Let us visualize all these concepts by using single image. Consider a scale in which concentration of Zn plus 2 is mentioned, along with change in Gibbs free energy and electrode potential. We know that concentration of Zn plus 2 increases during the reaction because of oxidation. So it may be 0.5 m, 1 m. So we never come across 0.5 m, but we know about the 1 m in standard conditions or standard electrode potential. So at 1 m we can visualize this, and as the reaction proceeds it becomes 1.5 m. So this system is having certain energy called as standard Gibbs free energy, that is delta G naught. How to calculate this energy? We can calculate it by using the standard electrode potential by the formula delta G naught is equal to minus NF E naught. Here we can see through an example, the zinc has the standard oxidation potential, it is 0.76 volt, and lithium has standard oxidation potential, it is 3.05 volt. We know delta G naught and E naught are directly proportional. So E naught for zinc and E naught for lithium. So here E naught for lithium is 4 times than the E naught for zinc. It means that lithium has 4 times more energy than the zinc at this condition. So we know that as the time passes, the energy present in this system starts to decrease by itself, and according to first law of thermodynamics, energy can neither be created nor be destroyed, but transformed from one form to another form. That's why this system transforms its energy by making zinc to undergo oxidation. So how much energy is transformed is equal to the amount of zinc converted into Zn+2, or the concentration of Zn+2 increased. So consider as the reaction proceeds, the zinc converts from 1m, 1.1, 1.2, 1.3, 1.4, 1.5m. We want to know how much energy present in this system. It can be calculated by using the formula delta G is equal to delta G naught plus RT ln Q. Here Q is equal to concentration of product divided by concentration of reactant. So here product is Zn+2, concentration is 1.5. If we put 1.5 here, we get delta G, which depends upon the delta G naught. And we can calculate delta G by using electrode potential. We know as the reaction proceeds, there will be increase in concentration, and also this value changes. It may be 0.80, it means it may be increasing, or it may be decreasing like 0.5 something. So whatever that value, we can use it and put it in the formula here, that is delta G is equal to minus NFE. Here E represents this. Corresponding delta G can be calculated. So by knowing this, we can calculate this. By knowing this, we can calculate this. But is there any relationship that by knowing this, we can calculate this, or by knowing this, we can calculate this? So we can calculate it, or we can derive the relationship between the electrode potential and concentration of the electrolyte. How to derive it? By using this relationship and this, and also this. So consider this relationship. Delta G is equal to delta G naught plus RT ln Q. We know that delta G is equal to what? Minus NFE. Delta G naught is equal to minus NFE naught. Let us put them. And here Q is equal to concentration of Zn+2. So minus NFE is equal to minus NFE naught plus 2.303 RT log concentration of Zn+2. So dividing by minus NF on both sides, which gives E is equal to E naught minus 2.303 RT divided by NF log of concentration of Zn+2. Here we must know that the reaction is oxidation. That's why this Q is concentration of Zn+2. But in general, we took reduction reactions. That's why this formula becomes E is equal to E naught minus 2.303 by NF log of 1 by concentration of Zn+2. Here we have taken reduction reaction. That's why Q becomes 1 by Zn+2, concentration of Zn+2. So this relationship is the link between the electrode potential with concentration of the electrolyte, other than the standard conditions. If we generally take any electrode, then E is equal to E naught minus 2.303 by NF log of 1 by concentration of m raised to n plus. This is called as Nernst equation. So Nernst equation is the relationship between the electrode potential and concentration of the electrolyte. Respect to factors affecting the electrode potential, we discussed about the electrode material. Second one is temperature. So with respect to temperature and the concentration of the electrolytes, Nernst equation is the solution, because Nernst equation is having both the factors, that is temperature and concentration of the reactants. With this knowledge, so let us proceed with our next concept. So consider it is NTP and we have a cell which is made up of electrodes. Both are copper, which are connected by salt bridge, but externally voltmeter is connected. So here the concentration of both the solutions is 1 molar. Then the question comes, what is the voltmeter reading? It is 0 volt, because at NTP, at 1 molar concentration of the electrolytes, both of them are having the electrode potential, that is standard reduction potential, of 0.34 volt. That's why this cell, that is E naught of the cell, is equal to 0.34 minus 0.34, which is equal to 0 volt. So this cell does not provide any electricity. But what if we change the concentration of one of the cell? But what if we change the concentration of one of the electrolyte? So here we increase the concentration. Then it is understood that C2 is greater than C1. It means the concentration on the right hand side is greater than the concentration on the left hand side. Then this cell is represented by the formula copper, which is in contact with Cu plus 2 solution, whose concentration is C1, which is connected to cell bridge, which is connected to again Cu plus 2 ions, but its concentration is C2, which is connected to copper. At this condition, the electrode with higher concentration starts to undergo reduction. So if it starts to undergo reduction, means it acts as a cathode. Electrode which is having lesser concentration will starts to undergo oxidation. So here the copper on the left hand side starts to undergo oxidation to give Cu plus 2 ions, whereas on the right hand side the Cu plus 2 ion starts to undergo reduction to become copper. Here both the materials of the electrode are same, but the concentration in which they are dipped in are of different. So such type of cells are called as concentration cells. Remember, this is a galvanic cell. So concentration cell is a galvanic cell in which both the electrodes are same material, but the solutions in which they dipped are having different concentrations. Now we get a question, what is the cell potential or what is the voltmeter reading? Again, we know that there is no standard concentration. Then we need to apply Nernst equation to this cell. So E of this cell can be calculated by the formula E of cathode minus E of anode. E of cathode is E naught of the cathode, that is E naught of the Cu minus 2.303 RT divided by NF log of 1 by what is the concentration of the cathode, that is C2. E of the anode is E naught of the copper minus 2.303 RT divided by NF log of 1 divided by concentration of C1, means left hand side. So E of cell is equal to E naught of copper minus 2.303 RT by NF log 1 by C2 minus E naught of copper minus 2.303 RT divided by NF log of 1 by C1, bracket complete. So here we are going to extract E naught of copper on left side. So E naught of copper minus E naught of copper, which will get cancelled. But here the minus of 2.303 RT divided by NF into bracket, this is log of 1 by C2 minus log of 1 by C1, because we have taken the minus outside. This gives here E naught of Cu plus 2, E naught of C plus 2 get cancelled. So minus 2.303 RT divided by NF into bracket log of 1 by C2 minus log of 1 by C1. So we know log of M minus log of N is equal to log of M divided by N. So minus 2.303 RT divided by NF log of C1 divided by C2. We know another logarithmic relation, that is minus log M is equal to log of 1 by M. So that's why, so here minus sign, it goes up, so it flips the C2 up and C1 down. So and at the end we get 2.303 RT divided by NF log of C2 divided by C1. So the condition must be known that here C2 indicates the higher concentration and C1 indicates the lower concentration. So C2 must be greater than C1. So overall we can say that E of cell of concentration cell is equal to 2.303 RT divided by NF log of concentration of the cathode divided by concentration of the anode. This is called as Nernst equation for the calculation of cell potential of concentration cell. We can conclude galvanic cell in a single video. So galvanic cell is a device which converts chemical energy of spontaneous redox reactions into electrical energy. Galvanic cell containing two electrodes connected by salt bridge, which can be represented by two vessels in which two different metals are in contact with their own electrolytes. Here left hand side is having different metal and right hand side is having different material. So left hand side it is anode and right hand side it is cathode. It is anode because it is having the negative charge. So the cell is represented as M1, that is the material of anode is M1, which is in contact with M1 raised to plus N, whose concentration is 1M. It is connected to salt bridge, which is in contact with M2 raised to plus 1 plus N into bracket 1M or whose concentration is 1 molar and which is in contact with metal 2. When voltmeter is connected, we know the condition is NTP and this concentration of solution in both the electrodes is 1 molar. Then this voltmeter shows the reading of EMF or E naught of the cell, which is calculated by the formula E naught of the cell is equal to E naught of the cathode minus E naught of the anode. So where do we get these E naught of cathode and E naught of anode? From electrochemical series. So as the reaction proceeds, there will be oxidation in anode, there will be reduction in cathode. So at the anode the concentration increases and there will be decrease in electrode material. In cathode the deposition of electrolyte material takes place, so there will be increase in material of the electrode. Then concentration of C1, it means it was before both are having the 1 molar concentration, but because of oxidation here the concentration of the anode increases, it is called as C1, but here the concentration decreases, it is C2. Now the cell is represented as M1, which is in contact with M1 raised to plus n, whose concentration is C1, which is connected to salt bridge, which is in contact with M2 raised to plus n, whose concentration is C2. It is in contact with M2. Now what is the voltmeter reading, which is indicated by the symbol E of the cell or cell potential. Electrode potential is individual electrodes, this is cell potential. So cell potential is calculated by the formula E of the cell is equal to E naught of the cell minus 2.303 RT divided by NF log of concentration of the anode or left hand side divided by concentration of the cathode, or E of the cell is equal to E naught of the cell. E naught of the cell we get it from the formula E naught of cathode minus E naught of the anode. So E of the cell is equal to E naught of the cell minus 2.303 RT divided by NF log of anode, concentration of anode is C1, concentration of cathode is C2, that's why log of C1 divided by C2. So this is called as Nernst equation. So concentration cell is a galvanic cell in which both the electrodes are of same type, but the concentration of the electrolytes in which they are dipped in are different. So consider a cell which is made up of same material. But if the electrolyte is having the same concentration, that is 1m 1m, consider it is maintained at NTP, then voltmeter shows the reading of 0 volt, because E naught of the cell is equal to E naught of cathode minus E naught of the anode. Here either it can be a cathode or it can be a cathode, so both are same. But if we increase the concentration of one of the electrolytes, then concentration of that electrolyte is greater than the electrolytic solution of other electrode. So here C2 is greater than C1. The concentration of this electrode is more. Because of this, there will be reduction. So the place where reduction takes place is called as cathode. So because of reduction, there will be electron consumption, which will create a drag through this wire. So the electrons starts to flow. So this in turn creates oxidation in the left hand side electrode. So the place where oxidation takes place is called as anode. So this cell is represented by M is in contact with M raised to plus N, whose concentration is C1, which are connected by salt bridge, which are connected to M raised to plus N, whose concentration is C2, which is in contact with M. So now it represents E of the cell. It is given by the formula cell potential, or E of cell is equal to 2.303 RT divided by NF log of concentration of cathode divided by anode. Here it is E of cell is equal to 2.303 RT divided by NF log of C2 divided by C1. This is called as Nernst equation for the calculation of cell potential in concentration cell.